I presented this work at LPSC. We've made a little more progress in the interim, but just in case you weren't there, we surprised ourselves with finding a correlation between topography and on and off swirl. That's the end game. So now you know what it's all about. So these are our study areas. We picked 2 regions in Mare, Ingenii. The initial goal of this project was to take a look at the photometric properties in these regions, seeing if we could see any textural changes in the regolith properties between on and off swirl. Now you see how we've defined on and off in these images. These are done by eye. It's bright, it's on, it's darker, it's off. I invite you to go see the poster this afternoon by Frank Chuang. We've now started applying machine learning tools for defining on and off swirl. These are very close to what the machine learning tools supply, but you might be interested in looking at that application. So part of the photometric process is to take your data sets and derive incident, emission, and phase angles that go with your reflectance values that take into account topography. And we do that using stereophotoclinometry. That's the same methods that's used to build shapes for asteroids. It's used for navigation for many missions. Part of what is made is a DEM, digital elevation model. And what you see here on your left are the images of the swirls. The color is the topography. And the person who does the stereophotoclinometry for us is John Weirich. And John handed me the top 2, the albedo and the topography. And I don't know what I had for breakfast, but I saw a correlation. Okay, I don't see it now, but for some crazy reason, I said, John, there's a correlation. And being kind, he said, but we then decided, okay, let's take a deeper look at this. What am I having with my Cheerios in the morning? So the first step to taking a look at this is, first of all, if you've got a slope like this and you've got a pocket, all right, if you want to define where your pocket is, you want to take out that regional slope. And that's what this step here. So we took the topography, we removed our regional slopes, and this is the result we have. The above is the albedo with the white lines demarking the different swirl units. Below is the slope corrected topography. And squint your eyes and see if you can see the correlation. We also masked out craters larger than 50 meters. And then what we did was we applied some statistical analyses. So before I get ahead of myself, this is real quick. On your right, you see the swirl feature. On the left is the unslope corrected topography. In the center is the slope corrected topography. So we did a statistical analysis of the data. What we did was we took the heights from each of the different units and we evaluated them using a Kuiper's variant of the, I'm going to mispronounce this, so forgive me, Kolmogorov-Smirnov test. We calculated mean heights for each subregion. We included propagation errors. We did cumulative distributions. I will show you some profiles that we took across the regions. And our analyses show that for our cumulative distributions, that we do have a confidence level of about 95% for the differences in topography we see. And so for our first area, our more southern swirl, you see one profile. So you see a lot of different information here. So let's start with the profile at the bottom. So what we did was we took a strip in this area. We did higher spatial resolution stereophotoclinometry, looked at the topography, removed the slope. And what you see here is a profile. You see it, the higher resolution topography is on your far right. The purple line is the slope. And what you see here is that on swirl, the median height on swirl is lower than what we see off in the off swirl. And as you get further out from the swirl, it gets a little higher. If you look at the cumulative distribution plots for the topography, which is plotted in the center, blue is the on swirl area. And you notice that the heights there are lower than what we see in the two off swirl regions. And it gets progressively higher as you go from the adjacent on swirl region to the next on swirl region. So it's like, okay, whatever I had for breakfast, it was there. So area B, same thing. We took a small strip, did a higher photoclinometry derivative of the topography. What you see, and that's shown on the right, you see the profile that we took. That's plotted at the bottom. The on swirl is, the mean values are lower than what you see off swirl, except for that little peninsula coming out. And our machine learning tools show us that that little peninsula isn't so much off swirl as it's part of what we call now a diffuse region. It's an intermediary between on and off. So once again, you look at the cumulative distribution plots plotted in the center, and the topography on swirl is lower than the topography off swirl.
We have 3 minutes remaining.
Thank you, Jacob. So in summary, we are seeing in these two swirl regions a difference in topography that's correlated with on versus off swirl. So now the question becomes, well, okay, you've got two examples. Show me more. Oh, well, let me back up a minute. So once again, why do we care? It is a clue as to the formation processes for these swirl regions. And one of the things we did in conjunction is to go look at mineralogy for these areas. These are taken off the Lunar Quick Map. They're the work of Lemellin et al. And Sato et al. And what intrigues us are the correlations with some of the mineral and oxide derivations. Now, the top in each column is just the reflectance of the swirl. So you know what is on and off. The quantity you see mapped is at the top. So you see olivine, then clinopyroxene, then you see orthopyroxene plagioclase, you see iron oxide, you see the OMAT parameter that measures maturity, you see the titanium oxide content. How do you get these mineral correlations with the swirls? Solar wind, retarding solar wind radiation isn't going to get you the mineral segregations. So it has us thinking about dust migration. The lows are pockets to capture dust, maybe, perhaps. To test this, we need to go look at other places. And so I'm just going to give a quick status report. We've got 4 other places we're looking at. We're looking at Reiner Gamma. We have the topography. We have the on and off swirl defined using our machine learning. We're in the process of doing the statistical analysis. You pick Reiner Gamma because it's the poster child for swirl regions. We're at the same place with Muscovines. Now, Muscovines is different because it has a weak field. It's our first example of a swirl with a weaker field. We have the stereophotometry DEMs done. We have our regions identified, and we're doing the statistical analyses now. Comments from Dave Blewett from the LPSC said, hey, there are swirls over these very rugged places. It crosses over really strong topography. Go take a look. So with Dave's help, we've selected this region in Gerasimovich and this region in Firsov. We just finished doing the stereophotoclinometry DEMs for them. Just to note that just to do a region like this in Pearsoft, that's like a month and a half's worth of work to derive the DEMs. So we've made progress since LPSC. The next step for these two regions is to apply our machine learning tools to define our on and off swirl regions and do our statistical analyses and see if what we see in Mare Ingenii we see elsewhere. So I'm going to end it with that.